this session of this afternoon, we have two invited speakers for one single talk, so double service for the same price in some way. So most of you probably know that our colleagues in Lisbon have a high collaboration with European Space Agency for several years, and two of them will be the invited speaker for this session, and one is a virtual invited speaker and the other one is a live invited speaker. The real one, yes. So Moitinho de Almeida is the virtual speaker, and he is working in astrophysics for several years, and he is leading this research with European Space Agency. He's also involved in many European networks in astrophysics. And our present speaker is Antonio Falcao, and he's also research engineer working with Rita in Lisbon. So I think that all the technical stuff are okay now, and we can go on for this talk. So the floor is yours.
Thank you.
Okay, thank you very much. I will start sharing my screen. I'm not sure if this is working well.
Perfect.
Let me see. Can you see me or the presentation?
Now we see you frozen.
Okay, so let me see. Share my entire screen. So this should work. So can you see now the presentation?
I think it's coming. So
Okay.
I think, Andre, don't worry. We'll just switch over to the PDF you sent me, and whenever you want to change slide, give me a signal, okay?
Okay, so you cannot see it.
No.
Wait, I can just try a second. And this way, can you see it this way?
It's much better.
Okay, so yes, so perhaps we better use the PDF I sent you then. I just reshuffled the order, but it doesn't really matter. So in that case, I apologize, but I have to get the previous version that I sent Antonio because I changed the order. So should be here, and I should have it here so that I know that we are talking about the same thing. Okay, fine. So thank you for your patience.
Andre, just switch over back to your camera, at least that way we can see you.
Okay.
At the moment we just see a blank screen.
Mm-hmm. Yeah, okay, so stop sharing screen. Okay. I can still do this other thing, which is instead of sharing the entire screen, it's just share a window. I don't know if this will work, but I believe not, right, Antonio?
You can try, it might work.
Well, okay, well, I'll stop sharing the screen and I'll just go ahead. Okay, Antonio, if you would be kind enough then to...
I'll be your pinch down here.
Okay, good. So this is the first slide, just a short presentation. So this is a work I'm presenting in the name of a consortium, which is composed of researchers from the University of Lisbon, from a spin-off of our group at the University of Lisbon, which is called Fork Research. It's a small enterprise company, Uninova, and the University of Vienna. So Antonio, please. Next. I'll just say next.
Next.
Okay, 2. So, well, first of all, we are talking about visualization of astronomical databases, big astronomical databases, and there is something about visualization that makes it different from other types of data exploration. And this comes because humans are above all visual things. Going next. And in fact, the neural substrates serving the visual sense, they occupy about 30 to 40% of the cerebral cortex, its total surface area. This means that we are in fact built physically for visualizing things, for understanding things through a visual channel. Next. And in its essence, astronomy, which is my main business, is an observational science. Tony, please, the next one. I should perhaps find a less irritating way to say next. And Tony, perhaps if I send you a sign on the Skype,
Okay.
like...
Yeah, we can do that. Yeah.
Okay, so I'll just keep on increasing perhaps the number. I'll start, when I press the 1, it means you do the next, and I'll go on 2, 3, 4, 5, okay? So, well, I hope you are seeing the slide in which we see a very old lunar calendar and a time series. Is this the slide you are seeing?
Yeah.
Okay. So, in fact, astronomy, as one of the oldest sciences, perhaps the oldest science, and visualization have been linked since, well, very ancient times. You can see on the left the oldest known lunar calendar. It's carved in on a bone, and it's really, really old. It's about 35,000 years before Christ. Then we can also see the representation of a time series. This is from the 10th or 11th century, and it's the inclination of planetary orbits as a function of time. Well, it turns out that, well, astronomy has evolved a lot since that time, and data is now growing in volume astonishingly. We have the Gaia mission, which is now happening. It's this hat-shaped satellite you will see on the upper right. This is an artist's impression. That will generate an archive of about 1 petabyte. You also have the ongoing, which is being built, LSST telescope, which is the Large Synoptic Survey telescope, which will also generate petabytes of data. You have above this picture of artist's impression of radio antennas, which will be the square kilometer array installed both in South Africa and in Australia, and that will be generating about an exabyte a day. The latest estimates say that it will generate per hour about as much as the whole internet traffic today, every day. So this is really a lot of data, and evidently not all organizations, or well, perhaps no organization will be able to handle and store these data permanently. But still, we generate it, we build these very expensive missions, and we want to study these observations. Just a further comment is that besides observing lots and lots of astronomical sources, billions and billions and billions, we also have repeated observations, because we will have time series, which will just contribute to increase the size of the data sets. Here in this slide I give you an example of some types of data we wish to observe. You will see I will not go into too much details, but just to show that it's very varied in kind. You will see in the upper right, well, images and zooms of these images. On the upper left, on the upper left, you saw that. On the upper right, you will see some spectra. Then you will see some scatter plots below, and you will see on the lower right a vector field overlaid on an image. In this next slide, we can also see that it's not only observed data that astronomers are interested in, but also simulations. And these simulations, using more and more powerful computers, generate so much artificial data that even though we control the experiments, we know what we put into the simulations, it is very hard to understand what is coming out of these simulations. And so, to understand these results, we also need to use exploration techniques, data mining, and in particular, visualization. So, okay, I've shown some examples of of possible displays of astronomical data, but I should go a bit further in being more precise of what do we mean when we say visualization. And Antonio, I hope you are synchronized. Do we have a slide that says in blue, visual data exploration?
Yes.
Okay, good. So one of our goals with the visual data exploration is to, well, have an overall view of contents of statistics or statistics of the data. But it's also used for quality assessments, for some zoom-in detailed views like producing maps and diagrams. But it's not only static. When we refer to visual exploration, we strongly mean also interactive. Research, knowledge discovery, interpretation of data is a trial and error process. So we must be able to interact with our visualizations, change it, move perspectives, navigation. We must also be able to interact with, not with the, only with the display, with the data itself. So we want to select data actually using the display, and we want to perform mathematical operations. And since we are dealing with many different dimensions, usually we can be thinking about dozens or even hundreds of attributes. We must also be able to see all these multidimensional data sets in some comprehensible ways, in a way we can understand. And perhaps the best way of doing this is through linking views of different projections of these multidimensional sets. We will go to this, back to this issue later. And of course, visualization is used for merging data, for fusion, and as I just said, well, analyzing the data in general. Besides exploration, scientific exploration, we also need visualization for presentation, for professional papers and talks, even for the general public, at the web, on the web, or through media, for TV, newspapers, or even presentation in public outreach talks. But it's also very important for decision makers and also for fundraising. If we want to convince a panel or a ministry to fund our research, it is always very advantageous to produce a good visualization of what we are going to deliver of our past results. Another aspect is also for collaboration. So we collaborate with each other, sharing visual results, and then we comment and iterate between us. And there is also the issue of storytelling, which I will go back further later. Okay. The final aspect I mentioned here is it's also about simplifying the data. Data is sometimes so complex that when we visualize it, we first produce a simplified version of what we have in the data and then present it. It makes it possible to transform things, structure, characteristics that are overly complex in the data into something more humanly graspable. And it is sometimes not just the end point of what we have to, of what we intend with our research, but just many times, very often, just looking at the data without knowing anything, it is even frequently the starting point and the guiding reference for our scientific thoughts. So let's be a bit more specific about what we are going to address in this particular project and our work that we are showing here. And so we will be talking about, well, representation of data through 2D, 3D plots. These might be scatter plots, histograms, multi-panel linked views, and we will have to deal with different representations of the data through glyphs, volumes, even taking into consideration advanced representations of uncertainty and other aspects. Develop? Yes?
Okay, sorry,
Antonio?
we just lost sound for a moment. Okay.
Ariel?
Just 1 second away.
Environment of astronomers, and so we had Paul, we have web pages in which we inquire the interested community about the needs and the use cases scientists will want, mostly related to this Gaia database. Of course, we also do some guessing, and interestingly enough, we have had some interdisciplinary projects with visualizations, especially with people related to earth sciences and disaster management. And we found that our needs are have a big overlap. There are different things too, but this already has resulted in common projects with these different communities, and even on an ongoing European cost action dedicated to this. You have a member in your room, Rita Ribeiro, which, if you are interested, can elucidate you more about this specific action. Regarding the emerging subject of collaboration in astronomy, this is something that is still in its infancy. It's not common, but we know that this is a tendency. Perhaps not in my generation, perhaps not in older generations, but we know that younger people, at least, are all constantly exchanging, communicating through Facebook or Snapchat or other things in which they are always sharing their thoughts. And we believe that in a few years these people will be doing their PhDs, and so they will be sharing their researches and any other scientific thoughts through these channels. So this is something that should also be taken into account when we consider interactive visual exploration environments. I show you in this slide an experiment done at Caltech a few years ago that has already ended, which is fun, but it also illustrated some issues with immersive, collaborative visualization. Actually, this is called MECA, which is the Meta Institute for Computational Astrophysics. It's based on a Second Life platform, and there, people had these rooms for virtual seminars. They could assist. People could actually use avatars to be immersed in the data. I am not proposing this kind of a platform, just calling attention to its existence, and that, playing with it can be fun, although right now we do not take it yet seriously in our development. So after this general presentation of the problematics around visualization of data sets in astrophysics, I will go a bit explain what this Gaia mission is that we want to analyze. So in a nutshell, Gaia is a cornerstone mission of the European Space Agency. It was launched in December 19, 2014, and it will measure positions, distances, motions, spectra that will allow us to get temperatures, luminosities, gravities, compositions, many attributes for more than 1 billion objects in our galaxy and beyond. These will be time resolved observations. So each object will be observed around 75 times, which will allow us to see variations in these objects. It will produce in the end an archive of the order of a petabyte, which is a lot. And so we will not be able to download the data to our computers. We will somehow have to bring the analysis systems to the data, and not the other way around. Just to call attention is that Gaia is going to be able to measure distances by measuring the effects of parallaxes, the parallaxic effects on these stars. So this is the difference of perspective that we have on the stars when the Earth is in different positions around the sun. And the positions that we are going to measure are so precise, around 7 microarc seconds, that this is really an enormous feat in engineering. Just to give you an idea, 7 microarc second is an angle so small that you could be measuring the thickness radius of a hair of someone that was located about 1,000 kilometers away. Or you could be measuring the size of a nail of someone that was standing on the moon. This is how precise it's going to be. Well, not precise, accurate, really. It's not even precision. It's absolute accuracy. So, the goal is, of course, that we can get very precise, very accurate distances and build a 3D map of the Milky Way, of our galaxy, so that we can understand its development and its structure. But still, these positions are so accurate that they will also provide us an absolute reference frame for our that will be used in our everyday activities. For instance, it will supersede the current reference frame that is used for GPSs, for instance. So when we think that sailors and travelers in the past would navigate looking at the stars, we today use GPSs and other machines for doing this, and we think that navigating through the stars is something of the past. This is not true. We still navigate through the stars because the GPS, the satellites we use for referencing, they use stars as for their own self-referencing. So they need accurate maps to know where they are and where they are pointing. So we still navigate through the stars. This is just an overview of what the machine is, what the satellite is inside. I will go through this one very quickly just to show that you have two big primary mirrors, and this is part of the secrets of why Gaia has such a high accuracy. It's basically two telescopes in a certain angle. And here it's also to highlight that it's a huge detector. If you have a CCD camera from your picture, from your normal photo camera, which is something small of the order of the centimeter, the big pixel camera of Gaia has a detector about 0.5 meter by 1 meter. It's really huge. It's about 1 billion pixels. And here is an image of the satellite itself with its solar shield folded. And Antonio, you can skip the next slide. Yes?
Okay. So
Antonio,
yeah.
skip the next slide and let's go directly to the other one saying the visualization challenges for Gaia and other big data.
Okay.
And you can also move ahead.
Okay.
Okay. So what will be the challenge for Gaia? Well, we have 1 billion objects. We have about 1 petabyte archive. So we already have challenges at the level of the hardware. We cannot store locally the data in common hardware available to researchers. Perhaps a few people can. We cannot also have it all, even if we don't store it here, we cannot just stream it constantly across the internet because we're limited by bandwidth. Of course, we could use tricks, like if we want to see the Earth, we can use tricks like detail on demand. This is simple in 2D, but it's completely non-trivial in 3D, and we will discuss if this is necessary or not. So this is it. This is the kind of hardware you would need if you wanted to examine interactively databases this size. But of course, not everyone can spend a few million euros setting his own individual structure, and definitely not here in your laptop. So the next one, please, Antonio. So the next challenge has not to do with hardware, but with the data and visual analysis itself. And the first thing we find is the data stunning, is confusion. We just have too many data to represent, and it's not easy to make sense out of it. So we need to find clever representations to try to address these aspects. Here you will see 3 different solutions for scatter plots that are for plots that are overly overplotted, that already suffer from overplotting. You will see on the left a hybrid of a scatter plot with a density plot. So the places where you can see individual points, they will be marked, but the places where you have severe overplotting, they are marked as a color code in which it's basically a histogram there. Then you can see on the upper right how transparency can help you also deal with regions of severe overplotting. And below, we can also zoom in with different kinds of lenses to capture details in different regions. And the lenses are really an interesting case. It would seem that it was just, okay, zoom in, and that's it. No, that's it. No, there are actually tens of different kinds of lenses that are useful for highlighting different aspects of our data. So there are whole papers just written on the subject of these magnifying lenses in visualization. One other aspect of this data stunning is the stunning across many dimensions. We will see a demonstration, perhaps if there is time, a film that has been provided through a link that Antonio will show. It's about 3 minutes and can illustrate this more. But if we don't, I just show you that if we want to see many dimensions, we should have linked views of different panels that will be showing different projections of the data, in which I should be able to identify data in one projection and have it highlighted in another projection. The issue here is that no software can produce all the kinds of views I would like to have and all the features I would like to have. So, besides having linked views within one single application, what we would really like to use is many different applications, the ones that best fit our particular needs for a certain representation, and then have inter-application linked views. And this is something that we already implement in our demonstrators. The next slide, please, Antonio. Okay. This is just a quick view to say that this thing about 3 dimensions, it really makes a difference. It really, when you have lots of data, you will see on the left that how data is projected, is flattened on the 2D scatter plots, and when you add one other feature, one extra spatial dimension, in this case, the structures actually pop out and you can see them. People do not use 3D a lot for scatter plots. They do for extended bodies because scatter plots put several difficulties in its manipulation, and especially in selection. But we are also handling this issue, and Antonio will show it to you later. You can skip the next one, Antonio. It's about Google Maps, just showing that detail on demand is easy in 2D. This is what we do in Google Plots, in Google Maps, but it's completely non-trivial in 3D. Because in 2D we can pre-compute several different resolutions of 2D maps and just zoom in and zoom out and provide the adequate resolution, the portion with the resolution. In 3D, we have infinite perspectives. So this sort of pre-computation cannot be done. It has to be done with a different approach. Completely non-trivial again, as I said. Next slide, please. So, Antonio, do we have a slide that starts in the word but?
But, yeah.
Okay, yes. So, how do we deliver 3D detail on demand? And how can we select arbitrary regions in 3D? Well, these are the issues we address in our projects. The first one was called CSI Vega, looks like the TV series, and just meant concept study for an interactive visual exploration of the Gaia archive. This has been completed. And then we had a follow-up, which is an ESA-funded project, which is interactive visual exploration of large data archives. It's about to end right now, and these are the demos we will show. Then there is one that is just starting that has also funded by ESA, which is more to do with the integration of different tools in a common integration and deployment in a common environment. Next slide, please. We can skip this one, and we can skip this one, of course. I think I'm being a bit, okay, so our line of work, we can also skip this one. I think I'm taking too long. So, and these are the use cases. Antonio, let's go directly to the one that says architecture.
Architecture,
okay. The other one was a bit the backbones on how we arrived to our architecture. So it's about how we build our requirements. It's a bit more interesting to the people that are wanting to build one of these systems, but it's, you know, saying how we arrived to a very long list of requirements and how we build the prioritizations. Okay, so to meet our needs, well, it's, as we hinted already, we must have something close to the archive, to the big archive, and this is what we call the server. We have a server-client architecture. So the server provides the visualization client, which will be outside, which can be a standalone application, which can be something in a web portal, simplified versions, digested versions of the archive. It is the object server that will provide the levels of detail that the client needs. And so this is what Google Maps would do up close to the data where the map is. And then we have several server plugins that we can add for performing specific needs for visualization. We have advanced indexing techniques, clustering techniques, and several the linked views capabilities are all within these plugins. And then we have the visualization clients, which I already showed you two of them when we saw this snapshot of these linked views. These were actually two different applications that were linked, and these have to talk remotely or also close, but mostly it will be remotely from the other side of the internet. They will have to talk to the object server. Antonio, next please. So we could have first the object server, of course, serving between the archive and our visualization client. In this case of this slide, we have an example of the CSI Vega clients. Next, please. Or we could have what we have right now, our preferred solution, which is having this server close to the archive, and then it can serve several users at the same time, providing the possibility of real-time interactive collaboration. And this server keeps track of all the different levels of detail he is giving to each client. This is already running at the ESA archive at ESAC in Madrid. So this is already serving a space mission, and we hope it will serve a few more. Next, please, Antonio. For more complicated situations, we could actually have two instances of this server, but I will not go too much into the details of this. So this is the basic idea of architecture. So the next thing is, okay, to show it working, really. So we have a couple of demos. Antonio will show a few more. I would suggest, I will not talk during these demos because it will be hard to synchronize what you are seeing with the movie, but they are annotated. So Antonio already has the link there to these demos, and he, I would suggest, would integrate this with his presentation, in which he will be showing all the interaction and how all these considerations are actually implemented and turn out. And I will be online and be glad to answer any questions you might have. And I stop here.
André, so I have the video here, the link that I just received is, do you want to play that video and
Antonio, okay, this is a general presentation. Yes, there is one with the linked views, and there is the other one which is showing our loading of, in this case was remotely, from our university here to a remote server, about 1 million points, I think. Miguel, our master engineer is right here with me, is confirming me this. Yes, 100 million points, yes, okay, in this particular example. Antonio, I think you could, they have about 3 minutes each, right?
Okay, so
yes.
Today we are just unplugging the laptop on which you are presenting, and we are plugging Antonio's laptop so that we can see the movies.
Okay.
You are out of the screen, but we are still hearing you very well. So
okay, good. I can see you well too. And so these are two films.
I just have one there called
you just have the other one, the one that Miguel sent earlier, right?
Consent demo. Yeah, that's the only one I received here.
SAP demo, okay, that is the shorter one. That will show you a demonstration of linked views.
Okay.
And now you should have received another one. Another
Okay.
link.
Not appropriate at this time.
Well, I think you can figure that out while we then see this first linked views demonstration.
Okay.
Just to make it clear that
But I'm just going to do the playback of the SAP if you want to comment on that one. And then, considering the time, probably I'll just switch over to the presentation I have here.
observatory.
Okay.
And there is the two applications we are considering. One is called Topcat, and the other one is called CSI Vega. So, or IVL, sorry. And so you can show this one, and the other link, I'm looking at Miguel, should be arriving to you. Should have received it by email, and now you can choose how you show them or not. It will take in total about seven minutes. So if it's too long to overlap with your presentation, please do as you find more convenient with the audience then.
Okay, we're just playing back here the SAP, which is the one that I received. The other one I have to wait for the download. So we're just playing back with that one. And then I'll probably switch over to the presentation here because we have around 20 minutes just to close this.
Okay. It's really fun. It's really up to you now.
Okay. So we're doing the playback of the SAP. Do you just want to give a quick idea of what's happening on this one? It's basically the link views and the mini-map functionality.
Yes. Well, I don't know in which stage you are, so it's a bit hard to. This is why we put the notes. So it was made to.
It's on 1 minute 20, and we see Topcat. So basically, I can just give an idea. So basically, this is a way for two tools. So this is one tool called Topcat, and that's used a lot by the astronomers. And on this side is the application that was developed by us within this project called Isabelle. And the idea here is to be able to link these two views. So when someone is exploring the data on one of the applications, they can see the same selected data points on the other application. And so these sort of things allow two totally independent tools which are communicating together. And basically the astronomer can then choose which one that they prefer to use for their own studies. So, okay, this is just a changing view of the modes. And so this is just going through the tool. I also have here a video which shows this a bit more in detail.
A comment, when you saw these maps on the left, like had a kind of flashlight on the right, these are mini maps, so these are different perspectives of the data, because when you are in the middle of these huge data point clouds, right now we are away, but when you are in the center, it's very easy to get lost in space, so these will give you always the reference. And now you are seeing different selections, how you select data in one application and you highlight it in the other one, either the 3D application or vice versa.
So the one Andrea was talking about are these over here. So these are the mini maps. Okay. I think there's a slight delay in there because the video on our side has already finished. And I'm going to go over to part 2 of the presentation, okay? Okay, so just switching over here to part 2. So, hello, thank you for the introduction. Definitely a different sort of presentation to at the same time. So I'm just going to give you here an idea more on the application side of things and how we're working. But first off, also here I think it's important a bit of context and why for us this sort of visualization tool is something that's very important as a decision support system. So We know that computers are excellent for number crunching, etc. Very nice. But sometimes visual recognition, it's complicated. It's a complex, and it has become itself a discipline. So, just a quick exercise. Quick guesses. What is this? Ah, excellent. So you don't need the context. But it might have been easier if I had put the other chairs there, so it allows you to identify. Why did you identify this so quickly? It's this, right? So it's basically the human brain is excellent in finding patterns. And this for us, the patterns in data, we all know that this is a way to transform data into information and finally into knowledge. And once you have knowledge, you have the power to take decisions depending on the situation where you're in. So this is just to put ourselves into context why the sort of visualization tools are important as a decision support system. So Andrea has given you the presentation on the Isabelle, so I'm just going to probably go a bit over that. But one thing that now I will focus on was how do we get these complex 3D selections done in this sort of environment. So there are some, let's say, some points which are important that we have to focus on. One thing is the interactivity. The tool must respond fast to the user. If we're doing data exploration, we don't want to wait 1 hour or go off to lunch and come back to see a result that I don't like. So interactivity is important. The correct representation of data is absolutely fundamental. So we can have things which give us a smaller representation, but it has to be correct. And the other point is not all of us have a computer cluster available to us to use on a personal basis. So having something working on our personal laptops and normal data interaction devices is a must. So this is a brief overview of what we've done in terms of the tool. So you can see here on the left-hand side, we have basically it's our data sources. So we have things coming in from the Gaia archive, as Andrea mentioned, lots of data coming in from these astronomical archives. We're really talking about astronomical amounts of data. All of these are coming either through the web or direct file interface, and then it's coming into our visual analytics tool. And by the way, this term visual analytics, when we actually started a couple of years ago on these things, and I mean a couple, like more of a handful of years, the term visual analytics was starting out. And but it really gives you a good perspective of what this is. It's really a visual tool that provides us means to analyze the data. And then on the right-hand side, we have these interfaces that we're using. So normal desktops, also mobile devices such as a laptop, and more nowadays our smartphones are more powerful than a computer, desktop computer from a few years ago. So all these devices we used to explore within this data set. So just some functionalities of the tool, and I'm just going to control myself here in terms of time. So one thing, our data is this 3D point cloud. So I don't know if you're aware of the 3D point cloud, but it's basically just an XYZ position and gives us a specific point on that space. When you're talking about interactivity and selecting things, it's very easy to compare this with computer-aided design where you're using a mechanical system, something like that. And it's very easy to create a selection. You just have to click. It's a solid object. It's easy to select it. But when you're talking about a 3D point cloud, the challenge is completely different because you have no solids. These are just individual points in space. And when you're looking at something here, it's an actual projection on the screen. So you have no depth awareness. So that in itself is quite a challenge. And so we had to explore as a way for the astronomers to look at this data and explore this data. We had to explore things such as these smart volume creation and editing, where we're actually looking at the depth axis. And we came up with several techniques adapted from some tools that we saw. nothing actually incorporated all of these things together. So that was one of the objectives, was also to find ways and just to join these all together. So we have things such as this, the interactive volume transformation, and I will then show you the demonstration. You can actually see it in action. But then we have these things such as brush selections, which allow us to paint a selection. And again, the depth awareness is complemented by intelligent placement. So we're analyzing using clustering mechanisms, for example, where is the data more dense, and that's probably where the user wants to select. So big data, that's one of the topics here. Big data analytics for decision making. So definitely we have a big data situation, just taking into account the volume. So you have big data situations where you're talking about the amount of data that's arriving in a short amount of time. In our case, time is a bit more relaxed, but we are having huge amounts of data, and as Andrea said, on future missions we're talking about exabytes per day. So that's really a huge challenge. So one of the things that we need to do is, on our current hardware, be able to support a large amount of data, and relatively large, 1 million points, for example. There's also obviously a limit, which is the actual screen resolution. If I plot, all these points individually, I just get a white screen. So that doesn't help anything. But at least we should be able to support them. We are supporting around 1 to 10 million points in memory. And then obviously that's just a small portion of our actual data set. So we're doing this dynamic data loading, as Andrea also explained, this details on demand. So while the user is interactively exploring the data, we are in the background loading and offloading data. And at the moment, we're running with 10 to the power of 9 objects. Each object is around 12, 13, 14 attributes each. So another very important point, if you're exploring, how do we interface with the computer? So one of the things that we did explore was a lead motion device. I don't know if anyone knows about it. It's been around for a couple of years. It's basically a more or less Kinect, but more precise. It gives you a very high resolution, and it's really basically for your fingers, not full body. So it gives us it's about a device this size, and it gives us let's say a cube, a volume over here of space where I control, and it has awareness of depth. So I have 3 axes along this. So it's $89.99, so it's relatively inexpensive. So this was something that we could consider for the project. We're not talking about a 3D cave, which would cost tens of thousands of euros. And it's something that allows us to do these 3D movement detection.
These are the things that people use in these V games, right? These interaction games for kids.
There have been, yes, there are some interactions on games precisely, and it can really detect 2 hands quite well. There are some situations of occlusion, but it can detect, and you can use it a lot for games. It's quite interactive, and as you mentioned, for kids it's fabulous. We've put them playing with our environment, just playing around and navigating in the universe, and it's really very nice to see them play around with it. And it's also very intuitive. There is one downside, is when you're actually trying to do work on it, we are, let's say, stuck in somehow in terms of interface. So we do need some sort of menu to be able to change modes, and either you go to your keyboard, traditional keyboard, to change mode, or we have to do these sort of, let's say, spatial menus, where I would do this with my hand and I'm selecting a different item. So that was one of the tools that we experimented with. And the other was an idea that we came up with, which was, okay, let's use a multi-touch device. And the first thing was thought of is a touchpad. But the touchpad will give us a multi-touch interface, okay? But we wanted to go one step further, and one thought was, let's use our smartphones. Why? Because it gives us a screen. And when we have a screen, we can do some quite interesting things. And having the screen itself to complement my own bigger screen allows me to be able to create my menus here. I can have an interactive area. I can also even visualize my data. So I can just make a plot of my own data and see it on my screen, on my touch device, interact with it, and then see that happening on the screen. So that was also one of the experiments that we did. So that is actually showing quite promising results, and yeah, obviously that's not quite visible, but basically we have here a selection, not enough contrast here, but basically we have a freeform selection that we do on our touch interfaces. That's the 5-minute mark? So much? Okay, that's fine. Perfect. Because movie time. And, whoops. So this is just a demonstration of the tool that you were seeing just a while ago, but this is a bit more focused in terms of the visualization and interaction. So this is running with a dataset from a mission called Hipparchus. So it's a slightly more reduced dataset, but the advantage is that we have color and volumes associated. So these are stars from our Milky Way galaxy. The colors itself are dependent on the star temperature, and the sizes are also relative. Of course, the scale would be incorrect if otherwise we wouldn't see anything because the data is so sparse. But here you can see the creation of a volume. So here we can create either a cube or just any normal polygon. And as you can see, this is real time. So we didn't accelerate the video in any way. This is just the user running through the data. So this for us was extremely important, that the person can manipulate the data and see the result immediately, so that they can make a better informed exploration of the data and then finally get the knowledge that they need. So this one here is demonstrating, and I'm sorry that the contrast is not good enough, but you can see the selections that are happening in the 3D volume, in the 3D environment. Sorry, am I blocking you?
No, it's okay.
Sorry. So you can see this is the brush selection, and this basically allows the user to paint what they want to select. And anyone who's been more interested, I can show you directly here on the laptop. But here is the freeform selection, and as you can see, it's in volume. So this then, I create a selection in 2 dimensions, and it's going to intelligently expand this into 3D perspective. And then, of course, something that from the scientific point of view is always important, I want to create an expression. So I can give anything above a certain coordinate or something like that. This tomographic view allows us also to interactively go through the data. And we found it to be a very interesting way. I mean, Andrea loved it from the astronomy side. They really enjoyed it. It's a very good way for us to see clusters in the data, because we actually see very dense points showing very, very easily. So it's a great way to explore that. And here we're also doing voxel rendering, so we're creating solids in these 3D point clouds. And as you can see, that's all in real time. And just as a detail, this is on real time and it's on my laptop, and this is just an ultra low voltage CPU. So it's not any expensive high quality or high grade hardware that we're running on. And we're doing something on like 60 frames per second, so it's quite interactive and it gives us a lot of fluid visualization. Here is just, that one there was just using a clustering mechanism, so we're also exploring that as a way to create more knowledge and exploring the data, so using a clustering algorithm called BD-scan. So, well, 2 minutes. This was another tool that thought that it would be interesting to show you, because this tool is also a visualization framework that was made also for ESA in the context of an ESA project, and basically gives us a map with several layers of information. And this is used, for example, by civil protection. This is actually from part of a simulation. I have a video as well, but we won't have time for that. But it's an interactive visualization of a flood happening in Lisbon. So you can see where the flooded areas are occurring, you can see the damage that is happening in the buildings themselves. So this can then be used also by the insurance companies who want to evaluate what are risky areas within the city if a flood occurs. So they're using this as a mechanism also for decision support. This would be, let me just a few seconds, but maybe I can just at least show you part of it running. So let me go, let's go to more or less here. So again, the idea of the linked views, so you can see not only the data that's going on here, you can see the, let's say, sample of the selection that's happening here. And then I can jump over time and see how this is actually being evolving over time. Let me see if I can find the right place, but my mouse disappears once in a while. Here. So you can actually see here the animation over time happening. As the flood is evolving, you can see the animation of the data points for this building that I selected here. So this is actually downtown Lisbon, and this is actually a flood that occurred. So it's a simulation, but then based on real data. So again, this is something that is used then by civil protection because we also included here a mechanism for them to, for example, evaluate emergency exits. See the distances that can be used for evacuating people from the buildings, and one thing very important, collaboration. Okay, this was the main thing that came out of this project was we need collaborative environments nowadays because of the way that we are geographically dispersed teams. So the idea of being able to insert just some points, some notes, and be able to share that with other people. So just ending considerations, just closing on 30 seconds. So obviously, just wanted to show you that visual analytics is an important tool for decision making. So it's not just exploring data and looking at nice graphics. It is, in the end, making informed knowledge of then being able to arrive at a decision. Obviously, in terms of big data that we're all working on, the interactivity issue is essential. We need fast reaction. And also it's a way to very effectively explore this unknown data. Really, data exploration is that you don't know exactly what is there. You can use algorithms which will give you some ideas, but it's very important to use our pattern recognition system to explore this data. And again, basically just as a final ending note, it's really the person, we're all talking about decision support systems, but in the end it's us humans that take the decision. So, thank you very much.
So thank you. I don't know if Andre is still with us.
I think he's still there, Andre?
The time is over, but I may imagine...
Yes, I'm here.
Okay, so thank you. So I may imagine that some of you have questions that are more urgent than the need for coffee, so we could go for one or two short questions.
I don't have any questions. I just want to thank you for the very nice presentation of your work with Isa and with the other presentations. Definitely the application of what you're doing is wide and the importance is well known and recognized. And there are a few other projects in EU which are in this direction. I'm not sure if you can exchange information with them, how much of this work with ISA is allowed to be open. I have a few ones that I can tell you.
That would be excellent because we are very open to collaboration, and even though we are aiming...
In this sense, I think you would help more them than they would help you because they are starting up the projects that I have needs. But in any case, it's also a learning process for everybody.
Yes,
It's collaboration.
it's collaboration, exactly. That's
So,
important. We have
Yes, I would like to make a comment.
Yes.
Well, thank you first for the appreciation. In fact, this is the usage is very broad. This has been already adapted And we forgot, actually, when I was just talking with our engineer, we could have made a demonstration of this system for visualizing space debris data. So the Earth is surrounded by space junk, and this has to be monitored, the orbits accompanied, and we have built a whole system that can go to the databases of space debris, bring the data, and then you can visualize, and this is also a hot issue for decision taking, because you have to know if you have to diverge the International Space Station so that a piece of space junk will not go against you, so it's an important tool for that too.
Yep.
Thank you.
I was going to mention that.
Yes, Jason?
Now, I am not an expert in the field, far from me.
Astronomy? Me neither. I'm not an expert either. We'll talk with them.
But you said something, if I understood correctly, that you can produce a map, let's say, of a segment of the galaxy.
Yes.
And you said that this was real time.
It was
You said that you can do that real time.
Yes, yes.
But time regarding space can be something relative. I mean, if we see a star now, we say it as it was 5 years ago or 6 years ago.
Even more. Yes.
You calculate the trajectories of the stars and produce actual real time, or the time we perceive.
In this sense, when I'm talking about real time, it's the real time interactivity of the tool itself. The data is, let's say, a snapshot of the galaxy. Because you're quite right. When we're looking at the stars, we're in fact looking at the past, and we talk about 5 years. If you're looking at the other edge of the galaxy, it's a few thousand million years. So I think we're right the director. I mean, from one end to the other, you're looking not in real time. It's what we're seeing at the moment. So Gaia, what it's producing in this data set is, let's say, several snapshots of this data. So when we're talking about here about real time, it's not the spar itself, it's our perception. So when I'm talking about the real data, it's in the real time, it's the real time interactivity of the tool. So when I move my mouse, I'm actually seeing it right now. So even though I'm manipulating a few 100 million points, I see it immediately, and not 1 hour later it suddenly moves. Because for us that's not data exploration. That will not allow you to explore the data in a correct way.
As usual, it's very surprising. We cannot imagine something else, but with the big data challenge that you have to address, it's actually a very significant contribution. Yes, I think that this is
A
really
huge
powerful.
challenge for
Yes,
sure.
I cannot imagine. So I think we have to conclude now, but we have still members of this project here.
And we will be here today, tomorrow, so feel free to come and talk with us. More details, feel free.
Okay, thank you to both of you.